I would like to talk about correct laboratory techniques when doing gravimetric analysis. Okay, these are the topics that I'd like to talk about in our lesson. First is the analytical balance, errors in weighing, general rules in weighing, and calculating uncertainty in weighing. Since we are dealing with gravimetric analysis, the most important equipment that we are going to use is the analytical balance. The analytical balance is one of the most sensitive weighing devices in the chemistry laboratory. It has a maximum load of 200 grams and a precision of plus minus 0.1 milligrams. The following is the schematic diagram of the analytical balance. The analytical balance has a weighing pan, which is located here. The weighing pan is here, and it is suspended through a string under the influence of a magnetic field. The weighing pan is located here, and as an object is placed on top of it, it will exert a downward force which pushes this compartment downward. So take note that we have a light source here, and if no object has been placed on top of it, this compartment here will totally block the light. But when an object is placed on top of the weighing pan, this will go downward and will allow light to pass through the null detector. The amount of light that has passed through is converted to a signal which will then be correlated with the mass of the object that is being placed on top of the weighing pan. There is no need to memorize the schematic diagram or the parts of the analytical balance. I just want you to know how it works and the mechanism behind its sensitivity. Since analytical balance is a very sensitive equipment, it can be affected by several sources of error in weighing. The first error is what we call the buoyancy error. Buoyancy is the upward force that is exerted by the medium upon the object and upon the weights. So take note that your object exerts a downward force on your analytical balance, but then buoyancy also exerts an upward force to it. Thus, a systematic error that results here is what we call the buoyancy error. In order to correct the buoyancy error, we use this equation, weight 1 or the corrected mass of the object, which is W1, is equal to W2 plus W2 multiplied by this density of air over density of the object minus density of air over the density of weights. This formula is used to correct the mass of the object when buoyancy is considered. If we examine the given figure, this figure shows the x-axis, this figure shows the density of the object versus the relative error in the y-axis. So as you can see, objects that have very low density tend to have higher percent error due to buoyancy error, and objects that have very large densities tend to have lower buoyancy error as a result, around 0.5 or 0.6. The percent error is around negative 0.25%. But then as the density of the object increases, the effect of buoyancy error lessens afterwards. So at around 12 grams per ml, the density is around 12 grams per ml, the buoyancy error is almost negligible. So take note that buoyancy error is mostly prominent if the objects that we are weighing has a very low density. Examples of those objects are volatile liquids such as alcohols, ketones, and other liquids. An example given here is a bottle weighing 7.6500 grams empty, 9.9700 grams after introduction of an organic liquid with a density of 0.9 grams per ml. So take note, this liquid has a very low density. The balance was equipped with stainless steel weights having this density. The question here is, correct the mass of the sample for the effects of buoyancy. So the answer is 2.322 grams. How was this calculated? Using this formula. So W2 is actually the mass of your object, which can be calculated by just subtracting these two quantities, minus 7.6500 grams, then plus same quantity, then multiplied by the density of air, which is 0.0012 grams per cm cube, over the density of the object, which is 0.992 grams per ml. ml or cm cube is just the same, minus the density of air, which is 0.0012 grams per cm cube, over the density of the weights, which is 8.0 grams per cm cube. The answer for this is 2.3227 grams. Take note that if we just take this W2 quantity, the answer is 2.3200 grams. This is without considering the effects of buoyancy to the object. But upon considering the effect of buoyancy to the object is actually heavier than what we expected. Apart from buoyancy error, another source of systematic error is the temperature effects. So errors in weighing an object whose temperature is different from that of its surroundings will result in a significant error due to what we call convection currents. Convection currents will exert a buoyant effect on the pan and object, resulting to a decrease in the weight measurement. Take note that the analytical balance is an equipment in which the weighing pan is covered with glass panels in order to block air currents which can cause erratic measurements. So what happens when you place a hot object on top of a sealed compartment? The answer is the air inside will become hotter. And as a result, it will cause a convection current which will exert a buoyant force on your object and on the pan. Furthermore, a hot object that is being placed on top of the analytical balance may damage the analytical balance. So warm air trapped in a closed container weighs less than the same volume at a lower temperature. The following figure, given here, shows the time after removal from an oven and the absolute error of the analytical balance. So as you can see, after around 1 minute, the absolute error is around negative 9 milligrams. Therefore, the object weighs lighter than its actual weight. Around 10 minutes, the absolute error is around negative 1.8 milligrams. And finally, after 20 minutes, the error is almost 0% or 0 milligrams. Other sources of error in the analytical balance. Okay. So these other sources of error are actually random errors only. Okay. Examples are readout fluctuations caused by air drafts, which cause erratic weight readings, defective voltage regulator. Analytical balances have an adapter when plugged into an AC socket, and they have these voltage regulators. Effective voltage regulator will cause readout fluctuations every now and then, and a porcelain of glass or glass object will occasionally acquire a static charge. Okay, that is sufficient to cause a balance to perform erratically. So if you weigh something on top of the analytical balance and the mass often changes, for example, at one point it's 0.1005, another 0.1006, another point is 0.1007, and then goes to and fro, back and forth. It may be caused by a static charge. So these are what they call random errors caused by readout fluctuations. Okay, what are the things that we must take note when using the analytical balance? We should not lean on top of the table to prevent fluctuation in the readout. That's one. Also, check the alignment of the balance as indicated by the bubble cap. Okay, so when you use an analytical balance, there is a bubble cap that is used to determine if the analytical balance is aligned properly. So if the bubble cap is at the center of your of the circle, so the bubble cap looks like this, and you have a circular area there. But if your bubble is around here, meaning the analytical balance or it's not aligned, so you have to adjust the left and right stands of the analytical balance until it will look like this. Okay, so the bubble is by the center of your bubble cap. of the circle that is drawn in the bubble cap. Finally, calibrate the balance regularly. Refer to the instructions manual of the instrument. So when you use the analytical balance, it will automatically calibrate itself. So no need to worry about this. General rules for working with an analytical balance. Bring the objects with you, objects that you will weigh. The spatula is it's like a small spoon that is used to weigh objects or transfer solids, tissue paper, record book and notebook, and some other objects that you might need. Beside the analytical balance, there is a logbook. So log in your name, date and time of the use in the record book. Also keep the balance and its case scrupulously clean. There's what we call a camel hair brush to remove spilled solid materials or dust and to remove static electricity or static charge. This can also remove static charge. Objects to be placed on the pan should be limited to non-reactive metals. Okay, take note that it should be non-reactive. Otherwise, it may corrode or it may destroy your analytical balance. Okay, this one is very important. Do not weigh sodium hydroxide crystals. Sodium hydroxide is a very reactive and it's a very hygroscopic. It's corrosive, it can destroy, it can damage your analytical balance, and it is very hygroscopic. It easily absorbs moisture from the atmosphere, and as a result, the mass that you weigh on top of the analytical balance will not be accurate because of its hygroscopic property. In your experiment, use tongs in holding dried crucibles and not your hands. Do not use your hands. Also, center the load on the pan. This one is self-explanatory. Use a clean spatula in weighing solids. And record the weight reading when the balance will stabilize for 5 seconds. So take note that when you weigh something on top of your analytical balance, it will not immediately stabilize. It will register different readings first, but wait for some time until the reading is stable. So those are the things that we have to remember when using the analytical balance. Before talking about our experiment, I would like to introduce about the gravimetric analysis of a soluble carbonate. So this one is not your experiment. Your experiment is determination of percent sulfur in a soluble sulfate salt. So this one is not your experiment yet. So these are the things that we are going to use for this type of experiment. So what we have here is you have a vial containing the unknown 217. You have 60 ml of calcium chloride, two 400 ml beakers and two stirring rods and hot plate. The hot plate is used to heat objects and liquids in particular. You also have beaker tongs and crucible tongs and also crucibles. Also, you have a desi-cooler which is used to dry your crucibles. So inside the desi-cooler, we have what we call desiccants. So these desiccants are drying agents. They are used to absorb moisture from the atmosphere. If you have purchased some shoes from shoe store like Nike or some other shoe stores, you might notice some desiccants that is placed alongside your shoes. So these desiccants are what we call drying agents. If they are color blue, meaning they are dry, but when they change color to pink or red, meaning they are very wet. So your crucibles are placed inside your desi-cooler or desiccator in order to keep them dry. Okay, so what is done here is the crucible is placed inside your desi-cooler and your desiccant, and altogether they are placed inside the oven to dry them. Afterwards, these dry crucibles are being weighed using an analytical balance. And take note, we have to use crucible tongs to transfer the crucible to the balance and not your hands. Because if you use your hands, the moisture from your hand will transfer on the surface of your crucibles. Furthermore, accurately determine the mass of the vial, contents, and the lid. Record the mass of the unknown. So this one is your unknown sample that is given to you. Transfer a certain quantity of the unknown sample on top of or inside your beaker and reweigh the vial accurately with the lid and record its mass in order to determine the amount of the solid that is being transferred. So this one is for this experiment. Top the remaining unknown into the beaker and label it. Finally, reweigh the vial afterwards in order to determine the amount of samples that are being transferred. What is being done here is adding some water to it in order to dissolve the sample. The sample here is a soluble carbonate salt. So what is being done is the soluble carbonate salt is being precipitated using calcium chloride in order to make calcium carbonate precipitate. So at this stage, the soluble carbonate salt is being dissolved using distilled water, and they are being heated atop a hot plate in order to completely dissolve your soluble carbonate salt. Okay. What is being done here is adding the precipitating agent, which is calcium chloride. So as you can see, the solution turned cloudy, which signifies the formation of precipitates. Stir the solution with its own stirring rod for a few seconds and leave the stirring rod in the solutions and allow them to heat for another 30 minutes. The experimenter waited until the precipitates settled and added a few more drops of precipitating agent to check whether or not the reaction has been completed, or to check whether or not all the analytes have been precipitated already. If the analytes have been precipitated already, meaning there is no more formation of precipitate upon addition of precipitating agent. But if when you added precipitating agent and you can notice some formation of cloudy precipitates, it means that the reaction has not completed yet. For this experiment, they used an ice water bath to aid the precipitation. Okay, so this setup is a filtration setup, particularly a vacuum filtration. So you have your crucible mounted here on top of your suction cone, and well, using the aid of a utility clamp to hold this setup all together, and your vacuum filter flask is being placed here, which is being connected to a vacuum pump using a rubber tubing. So this rubber tubing will cause a pressure difference in order to aid your filtration. So what happened here is the solution is being filtered using a vacuum filtration unit. The beaker has been rinsed and placed once again on top of your filtration unit. Furthermore, the crucibles are placed in a desiccant cooler and allowed to be dried inside the oven overnight. The next day, the crucible along with the dried precipitate is being weighed using the analytical balance. And the mass of your precipitate will correspond to the mass of your carbonates from your unknown carbonate salt. So you can calculate that using stoichiometric calculations that I have discussed in the lecture. Okay, so this one is another experiment which you will not be doing in the lab. Okay, so what we will be doing in the lab is this experiment. The title of your experiment is Determination of Sulfur in a Soluble Sulfate Salt. So basically, you will be given an unknown sulfate salt and you are asked to determine the percentage of sulfur in that particular salt using gravimetric analysis. So the materials for this experiment are the following. You have 4 pieces of porcelain crucible and cover. So this porcelain crucible is made up of a very sturdy material, and it can be heated even up to 1200 degrees Celsius. You also have a desiccator, wide mouth glass jar with airtight cap, and desiccants that are placed inside it. The reagents we are going to use are barium chloride solution, which is used to precipitate your sulfates. Precipitate sulfates as barium sulfate. We also have 0.1 molar silver nitrate, which is used to check for impurities that are being absorbed at the surface of your precipitate, and 100 ml concentrated hydrochloric acid. So the first thing that we have to perform in this experiment is constant weighing. So you only have 2 words here, but these 2 words is made up of several steps. Constant weighing means all these steps all together. And the next slide. Okay, so Basically, you have to clean the porcelain crucible and cover. That is self-explanatory. Label the bottom of the crucible with a pencil and write your initials and the crucible number. So this one is a very important aspect of your experiment. Many of my students exchanged their crucibles due to the fact that the labels were gone after the drying. Place the crucible and its cover in an upright position in a clay triangle and ignite the crucible using a strong blue flame from a Bunsen burner. The heating temperature would be 1000 to 1200 degrees Celsius. We must perform this heating for 10 minutes. So, what's the purpose of this? The purpose of this one is to remove moisture. So, this one is how you heat the crucible using your clay triangle and Bunsen burner. So, this one is your clay triangle. Of course, you have an iron ring, an iron clamp, an iron stand, and your crucible tongue. Use your crucible tongue when heating your crucible in order to prevent injury, because this one is very hot. So take note when heating using the Bunsen burner, you must align your crucible atop, slightly above this interface of your inner flame, since this is the region where the temperature is the hottest, or where the temperature is the highest. After heating your crucible, you have to cool it down for at least 2 minutes on top of your clean table. So clean your table properly and transfer the crucible and cover inside the desiccator and let it cool down for at least 20 minutes. So take note, inside the desiccator you have desiccants and the desiccants should be dried also. If they are not dried, you have to dry them by placing them inside the beaker and heating them on top of your Bunsen burner until they become blue. Okay, let it cool down for at least 20 minutes. We have to avoid weighing hot objects in the analytical balance in order to prevent systematic errors. Okay, weigh the crucible. Do not include the cover in an analytical balance afterwards. Record the weight and repeat the procedure until the difference in the weight is at least 0.0005 grams for three-way trials. This three-way trials does not mean that you have to take out the crucible once after weighing and then weigh it again after a second or so, and then take it out again and weigh it again after a second or so. You have to perform all the procedure from the beginning. So you have to perform this one, heating the crucible for 10 minutes, then these procedures. You have to do this 3 times. That is what is meant by 3 trials. Take the average of the 3 trials as the weight of the crucible. This figure shows the effect of temperature to the mass of your crucible. So basically, I have discussed this already. We should not weigh hot objects inside your analytical balance because it can affect the weight of your object, because it can lead to a systematic error caused by the convection current. So after constant weighing is the precipitation of barium sulfate. Ground your sample using a mortar and pestle and be careful not to spill the sample. Store the ground sample in a desiccator and weigh out accurately about 0.5 to 0.8 grams of your dried sample. 4 trials must be performed in the experiment. Okay, so take note that after weighing your sample, you have to transfer it. Transfer it, it's not written here, but you have to transfer it using a beaker. Transfer it on a beaker. Record the mass of your samples or of the trials and label the beaker properly so that it corresponds to the sample that is being weighed. So for example, in beaker 1, you have sample 1. You have to perform those type of things in order to track where is your sample going. So after transferring it on a beaker, dissolve each sample in about, take note, it's only about 200 ml of distilled water and 1 ml of concentrated hydrochloric acid. So for this one, you have to use you can use either pipette or graduated cylinder. Heat both the sample solution and the solution of your barium chloride nearly to boiling. How to do it? You can do it using your Bunsen burner. Okay, so this the steps for your precipitation. Pour the 25 ml hot barium chloride solution, of course, not quickly, it should be gently. Okay, the reason why we have to pour it gently is that we have to reduce the Q, reaction quotient, or the concentration of your materials in your sample. Of course, reducing the Q will also reduce the relative supersaturation. But carefully into the hot sample solution and stir vigorously. This one is very important. You have to stir vigorously in order to break the electric bilayer. Breaking the electric bilayer would result to lesser formation of lesser colloidal particles. So we don't want colloidal particles to form. Okay, allow the precipitate to settle and test the supernatant liquid for completeness of precipitation by adding a few more drops of the hot barium chloride solution. So take note that your precipitate should be settled down and the top layer would be transparent prior to addition of more precipitating agent. So if after the addition of your precipitating agent, your solution would turn cloudy, meaning the precipitation has not completed. So if that's the case, you have to add more precipitating agent and repeat the procedure above. After precipitation is complete, meaning no more formation of cloudy precipitate or cloudy solution, cover the beaker with a watch glass and allow the precipitate to digest for 1 to 2 hours, keeping the solution hot. Take note it's only hot and not boiling, which means 80 to 90 degrees Celsius over a low heat setting. What can we use here? We can use the hot plate because it's very hard to perform digestion using your Bunsen burner. You cool down the solution, cover the beaker with a shrink wrap, and keep it in the locker for the next meetings. This will further enhance the crystallization of your precipitate, meaning you have to wait for next meeting to collect your precipitate altogether. Or on the next meeting, collect the precipitate on an ashless filter paper. This ashless filter paper is provided by the lab personnel and wash the precipitate with hot water 3 times and test the last few drops of the filtrate for the presence of fluorides. This step is testing for chlorides. Chlorides are the ions that may be adsorbed by the surface. So you may have surface adsorption here. Wash the precipitate with hot water 3 times and test the last few drops of the filtrate for the presence of chlorides. Test the filtrate with 1 drop of silver nitrate, and if a cloudy solution would be formed, it indicates the presence of chlorides. So, if chlorides are still present, repeat this procedure over and over again. This procedure is to be repeated many times because you have to completely remove the chlorides that are adsorbed on the surface of your precipitate, or else the mass of your precipitate would not be the actual mass. After removing all the fluorides, okay, so this one is how to fold the filter paper. I have taught you this already. Mount your filter paper on top of your glass funnel and wet the sides with distilled water. Transfer your precipitate on the filter paper and wash the remaining precipitates using a wash bottle. So after testing for chlorides, you can place your precipitate inside your crucible. Remove your filter paper containing your precipitate and fold it like this and transfer it inside your porcelain crucible. Your porcelain crucible will then be ignited using your muffle furnace. This muffle furnace will ignite your samples or your precipitates inside. It will ignite the ashless filter paper and no ash will be remaining. Otherwise, the mass of your precipitate would be wrong. And I will be the one who will set up the muffle furnace. So place the crucible containing the precipitate inside the furnace. It should be slightly open as to allow air to reach inside the crucible. So I will be the one who will be setting up this muffle furnace. The drying step would be around 30 minutes. The temperature is 110 degrees Celsius. The charring state should be for 1 hour, and the temperature is at 550 degrees Celsius. And finally, the ignition would be for another 1 hour at 800 degrees Celsius. After ignition, we have to constant weigh the crucible with precipitate. The constant weighing is the step that we have performed prior to our experiment. Constant weighing is by using your crucible, heating your crucible under the blue flame of the Bunsen burner for 10 minutes. Then, after this, you have to place atop your table for cool down for 2 minutes on top of your table. Then transfer to your desiccator. That would be 20 minutes. And after 20 minutes, weigh. So these are the final steps of your experiment. But you have to perform this 3 times. So it means that there are 3 trials for the 4 samples. So it means that you have to repeat from here, okay, for 3 times. So it takes a very long time to perform the constant weighing. Okay, so I would like to give a schematic diagram on our experiment about the gravimetric analysis, which is particularly the determination of the percent sulfur in a soluble sulfate salt. So basically, the first thing that we had to do was constant weighing. For constant weighing, what we did was we heat the crucible on top of Bunsen burner. The time was around 10 minutes. It was exactly 10 minutes, followed by cooling it down. The time was 2 minutes. The next step is placing our crucible inside the desiccator. It was for 20 minutes. And take note that in here, your desiccants must be blue, because if it's pink, meaning your desiccants are also wet. Another thing that we have to perform is after 20 minutes, we have to weigh crucible using your analytical balance. So you have 3 trials of weighing your 3 trials of constant weighing, meaning you have to perform all this 3 times. So after weighing crucible number 1, of course your crucible number 1 should already be labeled. After weighing it, you have to repeat it once again. It should be times 3. So constant weighing is to be done 3 times. So after constant weighing, what we have here is precipitation. So the first thing that we have to do is to prepare our samples. So ground samples using mortar and pestle, and transfer your sample container inside a desiccator, and also dry inside the oven. After oven drying, if your samples are not yet dry, meaning you have to oven dry it. And after oven drying, you have to take or weigh around 0.5 grams to 0.8 grams of your sample. So you have sample 1, sample 2, sample 3, and sample 4. For record the masses, record the weight. Furthermore, transfer samples to the beaker. So your beakers should also be labeled accordingly, such that in beaker number 1 should have sample 1 inside, or beaker number 2 should have sample 2 inside, or beaker number 3 should also have sample 3, or whatever you like it to be. Furthermore, add around, this one is around 200 ml of water, 200 ml of water, and this one is exact 1 ml of concentrated hydrochloric acid. So this one is exact, meaning you have to use either pipette or graduated cylinder. Then you heat on top of your hot plate for stir until dissolved. Well, hot plate or also Bunsen burner. And then after heating, or while still hot, add precipitating agent. The term here is gently but with vigorous stirring. So after addition of your precipitating agent, what we need to do is to let the precipitate settle down. And when they are settled, add a few drops of precipitating agent. Precipitating agent is your barium chloride, right? This one is to check completeness of precipitation. Still cloudy after addition. If yes, meaning add more precipitating agent. Then return here. If no, then proceed to digestion. No meaning the precipitation is completed. Okay, so what is meant by still cloudy it looks like this. Okay, so take note, your beaker must look like this, and you have your precipitates settled down here. And after addition of your precipitating agent, if some precipitates are formed, meaning the precipitation is not yet completed. So that is what is meant by this question, still cloudy. Because if you add a precipitating agent and there's a cloudy solution that is formed afterwards, meaning the precipitation is not yet complete. You have to perform this step over again. Upon digestion, what is being done in digestion is just let the solution sit on top of hot plate. And take note the temperature is 80 to 90 degrees Celsius and not boiling for 1 to 2 hours. This one is very important. The time and temperature is very important. After that, cover with plastic cellophane and keep inside your locker. Of course, collect it in the next meeting. Okay, in the next meeting, what's being done here is your the precipitate is being collected. So the first thing that we have to do is to mount folded filter paper on a funnel and pour the solution until all the precipitates are collected. So when all the precipitates are collected, test for presence of chlorides. Take note that what we have here is barium sulfate precipitates, but then on its surface are impurities that are absorbed. So the process that co-precipitation is called surface adsorption. And we have to remove the chlorides by adding hot water and not boiling. So add hot water. Take note, it should not be boiling. Okay, so let me illustrate it to you. It looks like this. And your funnel might look like this. Your filter paper should be like this. And your precipitate should be here. So if you add hot water, some hot water would flow down here and collect this hot water using a test tube. Collect filtrate and add 1 drop of silver nitrate. So if the filtrate turns cloudy after addition of silver nitrate, meaning you have to redo this procedure. So let me draw another test for chlorides. For testing for chlorides, add hot water, collect filtrate, then add 1 drop of silver nitrate. Still cloudy. Yes. No. So if it's still cloudy, you have to redo this over and over again until it's not cloudy anymore. So if it's not cloudy, fold your filter paper and place inside your crucible. Then after this step, we can ignite precipitate using a muffle furnace. I will be performing this ignition. I'll just collect your crucibles and then I will ignite this all together. And finally, collect your weigh your constant weigh. That's very important. Constant weigh your crucible with precipitates. Take note that constant weighing is a very pedantic process. So it means you have to heat on top of Bunsen burner for 10 minutes, and then cool down 2 minutes, then desiccator for 20 minutes. It's a very long process. And then weigh, finally, using the analytical balance. So basically, this one is the schematic diagram for your experiment. It takes a very long time to perform gravimetric analysis. But after determining the mass of your precipitate, you can finally calculate the percentage of sulfur in your unknown sulfate salt. And the percentage of your sulfur would be, well, of course, you have to calculate the mass of your sulfur first. Grams of your sulfur is equal to mass of your precipitate, which is barium sulfate, and then multiply by the molar mass. So take note that 1 mole of barium sulfate is in grams of barium sulfate. And the mole ratio of your sulfur and barium sulfate. So 1 mole of barium sulfate has 1 mole of sulfur. And finally, multiply with the molar mass of your sulfur. So 1 mole of sulfur is some grams of sulfur. And finally, you can get the, upon cancellation of the units, you can get the mass of your sulfur. Percent by mass sulfur would be mass of your sulfur over the mass of your sample multiplied by 100%. Finally, you can calculate the mass of your percent sulfur in your sample. So this one is by using the stoichiometric calculation. If you use the gravimetric factor, then you can just calculate it like this. Grams of sulfur is equal to grams of your precipitate multiplied by the molar mass of sulfur and molar mass of barium sulfate multiplied by the gravimetric or the stoich mole ratio. So 1 mole of sulfur is also corresponds to 1 mole of barium sulfate because you only have 1 atom of sulfur here. So it's 1:1. Finally, same formula for percent by mass sulfur. So altogether, we can write this formula as like this. Percent sulfur is equal to mass of your barium sulfate precipitate multiplied by the molar mass of sulfur over molar mass of barium sulfate times the mole ratio over the mass of your sample times 100%. So this one is the consolidated formula to calculate the percent by mass sulfur in your sample.